Now here's a theorem that's fairly obvious, especially if you don't try to generalize it, but like as a tactical move, it's useful to be aware of as the shape of an argument. So let f be a real function that's continuous on the interval a to b. Then on this interval it must take all values between f of a and f of b. It's often used existentially, saying that a particular function value that we like must be attained. It's called the intermediate value theorem. But this is obvious, right? The function is continuous. Just look at the picture. Well, yeah. So if you can reduce your problem to this, you're done. Let's keep it simple. Say you're given a bounded object in 2D. Then for any direction, there exists a line that cuts the object precisely in half by area. Proof. Sweep the line over the plane and consider the function of how much of the object's area you've swept over. This is a continuous function that goes from 0 to 100%, so it must be 50% somewhere. Okay, maybe that was a bit lame, but this cutting thing can be generalized to n objects simultaneously in n dimensions, and this gets you the fabulously named ham sandwich theorem. Look it up sometime. And you prove it with a bunch of applications of the intermediate value theorem. That's one way to do it anyway. But let's end this video instead with a different application. I had heard of this before, but I had never realized it's quite this easy to prove. Theorem. Let f be a continuous function from the sphere to R. Then there must exist a pair of antipodal points, points opposite each other on the sphere, that have the same function value. Proof. Take an arbitrary pair of antipodal points p and q. If f of p equals f of q, then we are done. Otherwise, let d be the difference. Now, pick a great circle through both points and rotate them along this circle. After half a turn, they have swapped places, so the sign of d is flipped. Then, by the intermediate value theorem, somewhere along this rotation, d was 0. QED, these are your points. You can even do this for two functions from the sphere to R, and if you generalize that even further, you get the Borsuk-Ulam theorem, but I'll let you look that one up on your own.